session by Professor Luca Peliti. He'll be continuing with the lecture 2. So, like yesterday, we can have a short break after 45 minutes for 5 minutes or so. And then the idea is come back after the break. You can stay here because it's not a tea break. Tea break will come after the lecture. So then you can actually think about the part that was covered so far and then ask your questions after the 5 minutes. You have to clarify. So like yesterday, please raise your hands if you want to ask a question, and one of the organizers will give you a mic and then you can ask your question using that, so that Professor Peliti can listen.
In between also, you can ask.
Yeah, please raise your hand in between, and then if if you raise your hand, you can give you the mic and then you can ask your question. And the second thing is, after this session, we'll have a photo session just outside, just before the tea break. So please join, all of you. Okay, so with that, I would like to welcome Professor Peliti for the second lecture. And hi, Luca. So please.
Okay, so I'm going to give 2 lectures on the thermodynamics of information. This one is a more general, and the second one will be more focused on the information handling and biological systems. So let's start from, so the link between entropy, so thermodynamical entropy and information, in fact, goes back really to Boltzmann and Gibbs, who realized that the entropy is a measure of the disorder, or if you like, of the lack of information we have on the details of the state of the system. And this immediately begs the question whether the second law is something that is related to, say, properties of nature, or something that is related to our knowledge of the system. So this is sort of a question which is also being debated for a certain time, and is related in some sense to the deep question of the interpretation of probability. You know that in probability there are 2 schools that are facing. One is the von Mises school that says that the probability is something that is related to the actual frequency of occurrences, and the other, the subjective point of view on probability, that is due to Ramsey and De Finetti, that tells you that no, probability is just a way of stating in an objective way what is our knowledge of a system. So we are going to discuss these things in just a much narrower setting, seeing if, for instance, if really the manipulation of information, for instance, in computing, necessarily requires dissipation. And there has been essentially Bennett has discussed about this point quite a lot. And we see that, in fact, if you really wanted to have a practical way of handling information, there is some way of evaluating what is the minimal dissipation that is needed for this manipulation. And so that means that there are physical bounds on the efficiency of information handling. And this can be approached by a stochastic thermodynamics. So let's start from the Gibbs formula for the entropy of a system at equilibrium, so statistical equilibrium, that is given by this expression in which you see, so it is the sum over all microscopic states of the system of the probability of the state times the logarithm of this probability times the Boltzmann constant with a minus sign, so in order to have a positive quantity. And this is, so in the 48, Shannon introduced the entropy of a probability distribution, which is essentially the same expression, except apart from the constant, that was defined in such a way that, say, it's a reasonable way of measuring the amount of information that is contained in the probability distribution of a given system. And of course, now we can use this Shannon interpretation to define a non-equilibrium entropy for a system, so out of equilibrium, by simply using the Shannon entropy and in units of the Boltzmann constant. Of course, there is a problem with the non-equilibrium entropy, because if we take, for instance, a mechanical system, and we evaluate the same quantity, but evaluate it as an integral rather than a sum, of course, then what you have is that for an isolated system, this quantity does not change with time. And so it cannot be reconciled per se with the second law. What we're doing is just throwing this under the carpet again. We assume that it is possible to define this non-equilibrium entropy for the system you are considering, and these systems, as we have seen, they have a dynamic that is determined, that is a stochastic, and in fact, in which you lose, in some sense, information as time goes by. Okay, now let us see what, if we have defined the non-equilibrium entropy, we are able to define the non-equilibrium free energy. I don't know how to minimize this. The non-equilibrium free energy is simply by, you have a system with a given energy function, say the energy give for any microscopic state. You have an arbitrary probability distribution over the microscopic state, and assume that the system is in contact with a single thermal reservoir at given temperature T. Then the non-equilibrium free energy is given by this expression, that is the average value of the energy of the system with a given distribution minus KT times the Shannon entropy of the equilibrium distribution itself. And this has to be compared with the usual description at equilibrium would be just the average energy at equilibrium minus T times the entropy. So this is in fact, this quantity here, KH, is again the non-equilibrium entropy. And then you have a result that given a system, say, if you're given a system in which is in a state described by a probability distribution P0, and you transform it by some means to probability distribution P1, then you have to perform on the system a certain amount of work that is not smaller than the difference of these non-equilibrium free energy. I remind you that in stochastic thermodynamics, the work is considered positive if it is performed on the system, and negative if it is released by the system. Now, it is interesting to derive this relation.
Dr. Peliti, can I ask a question?
Yes, please.
So I'm just trying to understand this non-equilibrium probability. So is there a time in this P of X, or so how do I calculate this P of X for a non-equilibrium system?
Well, P of X in general, for instance, if we have a systems that we have considered before, P of X is this quantity that satisfies a master equation. So you start from
the P of X comma T.
Hmm?
It's a P of X in time.
Yeah, P of X can, in principle, can change in time. But now we see that P of X is given by the information you have on the system. And so it will depend on the kind of manipulations you're doing. And in particular, in the case of information handling, a P of X is a way of encoding the information that you have on the system and that what you want to have. So in general, from the time being, say that P of X is something that is given, maybe it evolves by itself, or it evolves, or it is given by the preparation of the system. I'm not going to discuss how it is done for the time being. And then you just imagine that you have a system that is provided in some given probability distribution P0, and then you want to manipulate it in order to have a distribution probability P1. Then you have this relation. It tells you that there is a minimum amount of work that you have to perform on the system in order to change these probability distributions. All right? Okay. How do we derive this? Well, what we know is that the total change of the entropy of system plus reservoir must not be negative. Therefore, 0 is less than the change, total change in the entropy, system plus reservoir. So this is the change of entropy of the reservoir. This is a change of entropy of the system. Now, the change of entropy of the reservoir with our hypothesis is given by minus the the heat that is received by the system divided by T, plus and here we have the change of entropy of the system. Now, by the first principle applied to the system, we know that the heat received is given by minus the change in the energy of the system plus the work performed on the system. And so we have this relation. And since this quantity must be positive or 0, what we have is that the work performed on the system must be larger than the change of the energy of the system minus the change of entropy of the system, that is, the change of the non-equilibrium free energy. Now, how is there a way of saturating the bound? Well, there is this way. Imagine that you are given this probability distribution P0 for each state X. Then define a model Hamiltonian is defined in this way. It is such that this initial probability distribution has the form of the Boltzmann distribution with a given Hamiltonian. So this is just a definition of this fake model Hamiltonian that describes the distribution you start with. And of course, here there is a sort of free energy that is related to this Hamiltonian in the usual way. It's just minus kT times the log of the partition function of this fake Hamiltonian. Now imagine, now you have a system, it is in this probability distribution, and you perform a sudden transformation. That is that you start, instead of having the original Hamiltonian, the original energy function E, you change this energy function in one step to this fake Hamiltonian. In this way, you are performing work on the system, but since the state of the system described by the probability distribution is not changing, then the heat, there is no heat exchange in this step. So in this way, what you have is that now the system is in some sense at equilibrium with the new energy, function. At this point, you can change the parameters of the Hamiltonian slowly, reversibly, as say, very, very slowly in such a way that at each time you can assume that the system remains in the probability distribution for the instantaneous value of the Hamiltonian until you reach a Hamiltonian H1, which is defined exactly in the same way, but now with respect to the probability distribution P1, which is our target distribution. So in this, what you have in this way that has been, you have, since the transformation is reversible, the entropy does not change. But what you have, but there will be a certain amount of, there will be a change in the value of energy, and then some heat will be released by the reservoir. So what we have is that the total change of the entropy of the system plus reservoir is zero because the transformation is reversible. Therefore, the Q, which is so the energy released to the reservoir, is equal to the difference, and so Q is the energy released to the system, is given by T times the change in the entropy of the system, starting from the initial state to the final state.
Hello?
Yes, please.
Okay. So when you talk about free energy, in the equilibrium systems, free energy means like the minimization of the free energy will give you the equilibrium state, then the structure, then the derivatives of the free energy will give you the correlations, etc. So all these features of free energy can also be associated with this particular non-equilibrium free energy as well, so that it can predict the
well, the equilibrium free energy is very particular because it satisfies a variational principle that we are going to derive. That is that given the constraint, the equilibrium free energy is the smallest one that you can have.
Yes. Yes. So
that is, but otherwise, I mean, as you see, what we are doing here is a sort of change under the hood, the a non-equilibrium free energy into an equilibrium free energy for a different energy function.
Okay.
So in principle, there is a complete equivalence in the sense that if you're given the free energy, then surely there should be a Hamiltonian for which the same system has exactly this value of the free energy.
Okay, so the thermodynamics related to the free energy in equilibrium, like those properties, modulus, etc. So they can also be at least in principle calculated in the non-equilibrium conditions from this non-equilibrium free energy.
Oh, calculating that is a different problem because it depends on, say, here you have a probability distribution, and the probability distribution, we don't know. Let's put it another way. If you start with a simple Hamiltonian E, yes, then this H0 for a distribution that is out of equilibrium can be very, very complicated.
Okay.
Can be non-local, for instance, and in general will be non-local.
So for calculating stuff like that, the free energies, the only free energy is not enough. You need to have a probability distribution, which is in general not known in case of non-equilibrium situations.
Yeah, for sure. In general, you don't know the probability distribution. So this is done on quantities that we don't really know for the time being, and then it depends on what you're doing with that. This is just a conceptual transformation that we are doing, and in fact, in general, what you have is that this H0, H1 Hamiltonians will be very complicated and probably very impossible to evaluate.
Okay. Yes. Yeah. Thank you.
Oh. Okay. Now we have a system that is in equilibrium with this Hamiltonian H1, and then we perform again a sudden transformation by changing H1, so the Hamiltonian from H1 to E, so that is the actual Hamiltonian of the system you are looking at. And then we have, again, there is no heat exchange, and there is some work performed on the system. This work is equal to the change in the energy on the average value of the energy with a given probability distribution, because the probability distribution itself does not change. And so this quantity is given by the average of the difference between the actual Hamiltonian of the system and this fake Hamiltonian for the final state. Then summing up, what you find is that you see that you have the contribution of the first step, which is the change in the average energy in the first sudden step. Then we have a contribution of the third step, that is this quantity here. And we have the change in the value of the energy between, say, the state P0 at equilibrium with the Hamiltonian H0 to the state at equilibrium with the Hamiltonian H1. And there is this contribution, so due to the, say, what we're doing here is expressing the change in the work in the second step in terms of the difference of the energy minus the heat released to the system that we have evaluated before. And so you find that everything cancels out except this contribution here, and of course the difference in the entropy. And this is equal to the difference, what you see is the difference in the non-equilibrium free energy between the final state and the initial state. So we have proved this relation between the work performed on the system and the difference in the non-equilibrium free energy. Let us now use this approach to see what happens in a Szilard demon. So in the Szilard demon, we can start from a situation in which you have, so we have value, we have a variable that describes the state of the system. I remind you that the system is made by a container that is divided in two equal parts. There is a single molecule, and this molecule can be on either on the left or on the right. So at the beginning, we say that, here we have that on this axis, we have the position of the particle, and on the y-axis, we have the information that we have. That is a bit of information that tells us if the particle is on the left or on the right. At the beginning, there is no measurement, so the situation is blank, but the particle can be on with equal probability on the left or on the right. After the measurement, what we have is that if the particle is, so the probability distribution is, say, along the diagonal, that is that the x and y are very strongly correlated. And therefore, most of the probability distribution is on, say, x equals L and y equal L, or x equal R and y equal R. But there is some error, and therefore there is a certain small amount of probability to be in the wrong case of this system. So in this way, we are starting from, say, complete blank to effect of a measurement, and in effect of the measurement is this pass here. You see that if we start from a blank slate and we arrive at this state, essentially the probability distribution has remained very concentrated in, so at the beginning it was concentrated just either on the left or on the right. And in this case, it is concentrated on the diagonal, so that in fact the uncertainty of this probability distribution over the false state is not much larger than the uncertainty of the probability distribution in the initial state. That means that if you start from a clean slate, then the measurement can be done without dissipation, at least in principle. Now, you remember that there is a manipulation, say, if you start from, once you know that the particle, say, is on the right-hand side of the container, you can perform a manipulation on the system and extract a certain amount of work by expanding, by letting the available space of the particle expand until it reaches the whole container. So that what it means is that you start with this, you start from this situation in which the probability is related to the diagonal, and at the end of the manipulation, you have essentially a complete uncertainty on whether the particle is on the left or on the right. Now you perform the manipulation, and then you set the wall in the middle, and then you don't know whether the particle is on the left or on the right. And that means that there is a completely loss of correlation between the bit that tells. Yes, please.
I still haven't understood what those boxes mean. Could you explain again?
Pardon?
I still haven't understood what those boxes mean. And those.
Oh, okay. I don't know if I can make a drawing. So the boxes are, we have a system which has 2 degrees of freedom. 1 degree of freedom identifies the location of the particle in the container. And that is X. The other degree of freedom is a bit that contains information about the location of the particle. All right? Okay. So so within each, and then the shade of the square that you find in the box, so it becomes darker when the probability associated with this state of 2-bit state is large, and is less than, say, it is gray if this probability is not very large. So what you have is that during manipulation, you start from a situation in which y and x are very strongly correlated, because all the probability is distributed on the diagonal. But then at the end of the manipulation, when you reset the wall in the middle, then this correlation is lost. And in fact, you have equal probabilities for all 4 states. Is that okay?
So there is just one particle, there are 2 particles. How many particles are there when you draw that box on the top?
How many?
How many particles do we have?
There is only 1 particle.
There's only one, okay.
There is only 1 particle, and there is one, say, device that stores the information about where the particle is.
Okay. So the particle can be either on the left or on the right.
Right.
Of the box. What is X and Y?
Yeah. So X is the location of the particle. At the beginning, it's either on the left or on the right. And then you perform the manipulation and you lose this information, because, of course, at the moment in which you end up in manipulation and you set the wall back in the middle, you don't know where the particle is. But the bit has remained whatever it was. You didn't change the state of your information device. Therefore, there is no more correlation between X and Y. And this is represented by the fact that all 4 states have the same shade of gray. And this is the effect of the manipulation. We have extracted some work by exploiting our result, our information, but then at the end of the manipulation, we are not back to square one, because at the beginning we were in some, we were here with a clean slate. So essentially at the beginning, there is no information in Y. And here we have completely lost the correlation. So now the problem is that you see, that means, again, what we have observed before, that the transformation of the Szilard daemon is not fully reversible, because you have to consider also the state of the recording device, that tells you where the particle is. And now you have to decide what to do with that. So one of the possibilities is that you want to reset the probability distribution to the initial probability distribution, which was a clean slate for as far as y was concerned. For instance, put everything on the left for y. And then and then of course equal probability for the particle to be on the left or on the right. So in order to do that, you see that you start with a probability distribution that is completely even for all four states, and you end up with a probability distribution in which only two states are accepted. That means that the non-equilibrium probability, non-equilibrium entropy of the system has been reduced by an amount that is kb log 2. You are reducing this entropy, and therefore you have to increase the entropy of the universe, in our case, the entropy of the heat reservoir, by at least the same amount. And that can only be done if you perform work and you dissipate a certain amount of work in the process. So this is summarizing. Now, in the initial state, we have x and y are independent in principle, or in the sense, for instance, that y is fixed at a given value, for instance, only left, and x can be either left or right with equal probability. Or you have the probability of x is given by some sort of equilibrium probability. When you perform a measurement, you introduce correlation between x and y, and you have therefore a change in the free energy of the system. Remind you that the system is given by the actual container plus the recording device that is described, whose state is described by y. So you have the change of the free energy of the system is given by, so the minus T times the change in the entropy of the system, and the change of the entropy of the system can be evaluated in terms of the change of the Shannon entropy of the system. And the change of Shannon entropy of the system is given by, say, two terms. So one term is simply the fact that there is a change in the actual entropy or probability distribution of the y degrees of freedom of the device, the recording device degree of freedom. And there is a contribution due to the mutual information between x and y. This is a positive quantity that tells you essentially what is the change in the probability distribution of the system due to the introduction of the correlations. Now, what we have here, what we have seen is that in this change in the entropy of the system upon measurement can be negative or zero, and that means that in fact that the change in the free energy is larger than or equal to zero, and therefore that the performance of a measurement will require a non-negative amount of work, and this is condition. Now, during the manipulation, that means that the probability distribution of x, that is now a non-equilibrium probability distribution, because you know where the particle is, can be relaxed to the uniform equilibrium distribution, in which it is with equal probability on the left and on the right. And due to what we have proved before, we can extract a certain amount of work that is larger than or equal of the change in the free energy during manipulation, and this is larger than or equal to the negative of the amount of information. This corresponds to the fact that you are, in a certain sense, erasing the amount of information you had on the system and on X. in the manipulation, and therefore you are losing this term here that is due to the correlation between your memory device and the actual system. And now you have the third step, that is a resetting. You want to take the distribution of the measuring device and bring it back to its initial condition. And in this way, what you have is that you have to reduce the probability, you reduce the uncertainty on Y to put it back to, say, a standard state. And in this way, you have the change in the free energy of the reservoir must increase by at least a kT times the change of the entropy of the device, and the change in the entropy of device is with a minus sign. So, and the change of the entropy of the device is in principle positive, because in this transform because you start from a distribution which is even between left and right, and you reduce it to, say, for instance, to the clean slate less. So that means that at the end of the day, what you have is that the change in energy of the reservoir must be larger of this of the change in the free of the change of free energy of the system, and therefore what you get is that the total amount of work that has been performed on the system must be non-negative. You can see that it does not depend on the. So here we define it in different cases. So if Y starts in a clean slate, as a clean slate that is in a well-defined state, it means that the Shannon entropy of the memory device vanishes. Therefore, the change in the entropy of the system upon measurement is given by this expression. So this is the probability distribution of the device after measurement. For instance, at the beginning, you know the memory device is, for instance, in state L. At the end of the measurement, it can be either in state L or in state R with equal probability. Therefore, this quantity, this entropy of measurement is equal to log 2. And then you have to subtract to this the fact that you have a correlation between the particle and the device that is represented by this mutual information. And this reduces the amount of entropy of the system. So this quantity, in fact, can vanish. If we start from, say, H equal to 0, then this measurement exactly cancel the correlation if there are no errors in the measurement. So using this, what you get is that the total amount of work that you can get is larger than the total change of free energy of the reservoir that is given by minus the KB times the change of the entropy of the system during the measurement. In the case of the gas experiment, this is what I said is log 2. So in the sense of what you end up is that this work is bound by log 2. So I put the other possibility is that you don't do a resetting. If you don't do a resetting, then what you have is that upon So you have a situation like that. Your initial state, instead of being y, instead of being simply L, now is can be L and R with equal probability. And therefore, we have initially a distribution which is completely completely distributed over a false state with equal probability. And then upon the measurement, we end up as before, but that means that in the going from the initial state to the state immediately after the measurement, the entropy of the system has been reduced, and in this case, you have to release a certain amount of heat to the reservoir in order to keep the total amount of the entropy of the system at least constant. So,
I have a question. So in the examples that you've found, could you say what are the values of the mutual information in those specific cases?
oh, okay. What is the value of mutual information? Let's see here. Imagine that there is no error. All right?
Yeah.
Okay. So now I should probably say the mutual information is given by the sum over. I should just a moment. I see if I can write on a tablet. Is it? A moment, sorry. Well. Or no, okay. I don't know at the moment. It doesn't. I don't know how to connect to the tablet at the moment. Okay, so what you have is that in this case, the mutual information is a no, see.
You can just probably say what the values are in these examples.
Okay, log 2. It's log 2.
And in the
Because we start with the situation. You start in this case. You have the chain. If you go, okay, the mutual information. If there is no error, so if these gray errors are not there, what you have is a mutual information simply log 2, because you have that the conditional probability is equal to the say the mutual information is given by the sum over all states of the probability of the all states p, x, and y times log of the probability of x and y, the joint probability of the two states, divided by the reduced probabilities, the marginal probabilities of x and y respectively. So in the case in which x and y are, say, are bound, what you have is that the p, x, and the joint probability is equal. So the joint probability is given by the marginal probability times the conditional probability. The conditional probability now is either 1 or 0. And so what you have is that you have to sum the log of 1/2 over these two states, and that gives you log 2. There is a minus sign, sorry. So in this case, the maximum mutual information is equal to log 2 in this case, and if there are some errors, then it decreases by a certain amount. I should really have written the expression before. So at the end of this reasoning, what you have is that the total amount of work that you perform on the system must be larger than or equal to. So these are the work performed on the measurement, or the work performed on the reservoir must be on the resetting. Sorry, on the resetting must be larger than or equal to the mutual information between x and y times kt. And in fact, what you have is that these inequalities can arrive from a fluctuation relation for the fluctuating work and the fluctuating mutual information. So here we have the definition of fluctuating mutual information is given by, so the log of the joint probability of x and y divided by the product of the marginal probability of x and y. So if we take the average of this quantity over the probability distribution of x and y, we obtain the mutual information that is up here. Now, this is a fluctuating quantity that is similar to the fluctuating entropy that we have seen yesterday. And we can use this to derive this integral fluctuation relation. So the integral fluctuation relation tells you that the average of the exponential of minus the difference between the work, total work performed on the system minus its change in free energy divided by kt minus the fluctuating neutral information here. You take the average of this quantity over any manipulation you're doing from the beginning to the end, and this relation is satisfied. We are going to prove this in the next slide. In general, you can use a situation, you can generalize this thing to the case. In fact, we are already using the fact that our decision depends on the results of the measurement. So we are using some sort of feedback control. So in general, you can consider that instead of a very simple manipulation that like the one we have seen, you have a general system in which you perform a manipulation according to the value, to the result of a measurement. And in this case, what you have is that this average. So if you take the average of exponential of the work performed on the system and the change of the free energy divided by kt will be given to this, will be equal to this quantity gamma that is in general less than 1, because it is the sum over the probability of obtaining measurement, of obtaining a certain measurement with a given manipulation. If you perform several measurements during a manipulation. But this I'm not going to discuss. So let's take the proof of this fluctuation relation that is quite instructive. So assume that you have a system whose state is described by x, and then you have a measuring time Tm, and then immediately after, so you have the value of x at Tm is equal to xm measurement, and then the measuring device gives you a result equal to y. Then you apply a protocol that it depends on y, depends on the result of the measurement. Now, for each value of the measure result, you can apply the Crookes relation that tells you that the exponential of the change in the entropy of the, say, entropy production over the say evolution of the system after the measurement divided by KB is equal to the ratio of the probability of the trajectory with a given manipulation that now depends on the result of the measurement, divided by the probability of the reverse trajectory with the reverse manipulation. And this is true for each value of the result of the measurement. Now, the joint probability of result of the measurement times the trajectory is given by the conditional probability of the state of the system at the moment of the measurement. So the probability, of the result of the measurement with the given state of the system at the time of the measurement times the probability of having this trajectory x if you perform the corresponding manipulation due to the value of the measurement. And so by the definition of the mutual information, we see that the exponential of the mutual information is given to is equal to the ratio of the conditional probability, the same conditional probability that is here, divided by the marginal probability of the measurement device. So you plug this in together and you find that the exponential, so the exponential of delta S, this quantity here, KB, that depends on Y, remember. And then the mutual information is given by this ratio of probabilities. So this is a conditional probability of Y given XM. This is a probability of forward trajectory, and this is probability of the reverse trajectory. And here we have the marginal probability of the measurement. So now you perform the manipulation that we had before. That is, we pull this up on one side, and we pull this on the other side, and so you pull this on the other side. And what we have is that here, this expression, that is a probability of the trajectory given the measurement times this exponential is equal to the actual probability of the reverse trajectory summed over all possible results of the measurement. And this is by normalization is equal to 1. Now, this can be exploited and has been exploited experimentally. And there is a famous experiment done, let's say, more than 10 years ago now, by Toyabi and other. The idea is to introduce some sort of a daemon that is able to say that allows to climb a staircase by exploiting Brownian motion. So the idea is that you have a particle that is, say, in a reservoir and is bound to state on a staircase. And of course, because of the thermal fluctuation, it will be sometimes it will go up one step, but most of the time it will go down, because simply because the energy is lower if you go down. Now, just imagine that you have a daemon that arrives, and if the particle goes up one step, puts a barrier and prevents it from going down. So you put the barrier and then you wait. One day or another, due to the thermal fluctuation, the particle will be able to go up one step. And in this way, putting barriers one after the other, you let the particle go up and up and up. So this is essentially the same idea, only that it is done on a system which evolves continuously. So the experimental setup is by linking a dimeric particle to a surface and immerging it in a solution, and then you apply to it electric fields In a way, it is possible to say to favor a certain orientation of the dimeric particle in two normal directions. So in this way, if you look at you have, and you can switch at will the direction of the electric field. In such a way, you have a two states of how to say, you have two different Hamiltonians, in fact. So one Hamiltonian in one Hamiltonian, the energy as a function of the angular position will be given by this sinusoid, and you see that this sinusoid has a ramp, so it increases towards the right. When you switch, you switch by say you switch by 90 degrees. And so you have a sinusoidal with the opposite phase. And the idea is now that you follow the evolution of the particle and you decide when to switch. So if the particle stays within a trough of the potential, you simply monitor it and you basically you don't do anything, you just keep it. But now imagine that there is some fluctuation by which it goes up in the potential in a certain region in the direction that is in the good direction. At this point, so just look at this the situation here. Before it goes down, you perform a switch of the potential, and in performing the switch of the potential, you trap the particle, so the particle is initially here. Just by fluctuations arrive at this point, you switch the potential and you trap it in the following trough, and then you wait for the next time. And of course, what you have to be careful is that to avoid the situation in which it climbs on the opposite side. So in this way, you can. So there are some regions of the particle, some regions of where the particle can lie, in which it is useful to switch. So this is the kind of behavior that you have, and it depends, of course, on the time that you wait between one switch and another. And so in what you have is that, well, let's say that this is the amount of work, this is the difference between the free energy change and the work in units of kT, and you find that there is a region of time in which you actually have that the work is that the work you get is larger than the change in the free energy. And when you get a slower and slower manipulation, then this is not the case. And you see this in terms of the trajectories. If you wait long enough before, so if you perform the measurements in long intervals, the particle will go down. If you perform a measurement faster, it remains more or less at the same level. But if you measure, if you monitor at a sufficiently high frequency, then you have the possibility of letting it climb up. So this is this is a situation in which the particle moves from one trough to the following one. So up against the ramp, against the potential. So we can now put it, how long do I have? Probably, so when did we start, sorry?
So we have Then about 50 minutes.
15 minutes. Okay, great. Thank you. Okay, so let's make a say more definite model of an information reservoir that is of the for instance of the device which records the position of the particle in the what we have discussed of the Szilard model. So what we have a system that can be in two, say, computational states, either 0 or 1. And so we say that the system is subject to a potential, and this potential has two minima, one at 0 and one at 1, at the same value of the energy. Then, of course, you have the system is, for instance, a Brownian particle, so it has some microscopic degrees of freedom, and these degrees of freedom fluctuate, and you have, say, you have an equilibrium probability distribution conditioned on the fact of staying in state 0, and then another possible equilibrium distribution in which you have state 1. So you have the computational degrees of freedom that in our case is just a bit, gives a 0 and 1. You have the microscopic degrees of freedom of the device, and then you have, of course, the heat bath degrees of freedom. And the heat bath degrees of freedom are at equilibrium at the temperature. So the microscopic degrees of freedom are phase space variables, but we are, say, assuming, because this must be an information storing device, we are assuming that, in fact, it will take ages for the spontaneous fluctuation to go over this energy barrier and go to the other state. So that, in fact, that you have some sort of ergodic component of the phase space of the microscopic degrees of freedom of the device, each associated with the information carrying degrees of freedom. We can then discuss what does it mean to perform a reversible transformation on a system like that. Of course, we have thermodynamic reversibility. Thermodynamic reversibility is related to the whole degrees of freedom of the system. We consider the total system made by the information degrees of freedom, the internal degrees of freedom, and the thermal reservoir as one thermodynamical system, and we perform on this eventually. We may perform a thermodynamically reversible transformation. So in this case, we don't, we have that the total entropy produced will vanish. Another possibility is we can discuss about a logical or computational reversibility. And we say, I'll discuss better what is logical or computational reversibility, but the basic idea is that a computation is reversible if, given the result of a computation, you can reconstruct the data where you started from. And the other possibility that we can consider is heat transfer to the bath. So in logical computational reversibility, this is connected to the entropy change in the measuring, in the information carrying device, that is the free energy, the computational degrees of freedom. In the case of heat transfer to the bath, what we have a change of entropy of computational degrees of freedom plus the internal degrees of freedom. So now thermodynamics implies that the total entropy production is not negative, and thermodynamically transformation are thermodynamically reversible only if the total change in the entropy vanishes. Now, in stochastic thermodynamics, we do probability, in general non-equilibrium probability distribution. And what we are seeing is that you can transform a probability distribution into another probability distribution, but in fact, what we have,
if you go back one slide, can you just explain once again what is this, the computational reversibility?
Pardon? I didn't
Can you
hear.
please explain once again what is the computational reversibility? There are two
Okay.
states, 0 and 1, and so what
Okay, computational degrees of freedom. Just imagine that you have a memory. No, a memory is, for instance, a transistor circuit which is bistable. So the system can be in two states. So and it is represented by a bit.
Okay.
But you have a mechanic. You have a whole a system which is made by a great number of atoms. The only thing you're interested in is whether the transistor is in state 0 or in state 1. But in fact, in each state 0, 1, the system is still a statistical mechanical system with its internal degrees of freedom. So I distinguish the degrees of freedom that carry information for a manipulation of the information and the ones that are internal. So if you like, say, in a memory, you have, so in a magnetic-based memory, you have a small amount, a small domain, which has a magnetization in some direction. The direction of the magnetization is the computational degree of freedom.
Okay.
And for each value of the degree of this computational degree of freedom, you have a probability distribution of the internal degrees of freedom.
Mm-hmm.
That is, of course, not overlapping with the probability distribution in the opposite direction, because otherwise you lose your probability, you lose your information. We do know, if you look at the tapes, videotapes, you know that videotapes disappear with time, and this is due to the fact that the magnetic domains get rearranged, and this would correspond to the situation in which the fluctuation of this microscopic degree of freedom is such that are able to go to the other side, and in this way you lose your information.
Okay.
Right?
Okay. Thank you.
Thank you. So again, say the idea is that you can transform a probability distribution into a different probability distribution only if the total value of the entropy of the system plus the reservoir is larger than 0, larger than or equal to 0. And where, say, the delta S is the change in the system entropy. And this is tantamount to say that the work that you perform on the system must be larger than or equal to the change of the free energy, of the non-equilibrium free energy of the system. And the reversibility of this process and going from one probability to the other only if is thermodynamically reversible only if the total value change in the entropy of system plus reservoirs vanishes. On the other hand, computational reversibility can be described in this way. Imagine that you have, your device has a certain number n, small n, of computational degrees of freedom. So it is a collection of n bits. And then a computation is a transformation of x into x prime, a different configuration. Now, the computation is computationally reversible if x prime and x, so if you can reconstruct x given x prime, that is, if x is a one value of x prime for all x prime, that is, for each value of the result, you have a unique value of the data. I gave you some examples. For instance, the transformation goes not, x goes to not x. And of course, is reversible because then x is given by not x prime. On the other hand, erase is the transformation that sets the bit to, say, 0 for everybody. And of course, it is not reversible. Once you know that the result of the computation is 0, you don't know whether you started from 0 or 1. In general, if you have a 1-bit Boolean function that is two bits are entered and 1 bit comes outside, this is not reversible. You're not able to reconstruct 2 bits from a single bit. On the other hand, you can have a 2 bits to 2 bits mapping, and some of them are reversible. For instance, exchange, in which you just exchange the 2, that can be undone by simply repeating it. Now, in general, we say that a deterministic computation is computationally reversible if the Shannon entropy of any probability distribution on the initial state, on the data, is equal to the probability distribution of the results. Because in this case, you can imagine that there is, so this is, say, it is sufficient for this to happen that there is a one-to-one mapping between x and y, x prime. In general, computationally reversible transformation reduce the entropy of your device. So the idea is that at this point we are mapping something that is related to the computation degree of freedom to a sort of statistical description or statistical mechanics description. So we go from the logic to the to information theoretical distribution, theoretical concept, and of the entropy, Shannon entropy of the distribution. So, for instance, let's see how we can perform the erasure transformation on the Szilard engine. So in the Szilard engine, we have initially a system that, so we have this our container divided in 2 parts, and the particle can be either on the left or on the right. And we want to reduce, say, we want to erase this uncertainty on the position of the particle. How we do it? Well, what we do is that we remove the wall that separates the 2 parts of the container. We put a piston on one side, and then reversibly in the sense of thermodynamics. So very, very slowly, we push the piston until it reaches the middle of the container, and at that point we reset the wall. In this way, we started from a situation in which a probability distribution was equally distributed between the left and right, and we end up with a probability distribution which is concentrated on the left. In this way, we have reduced the entropy of the system by log 2, by KB log 2, and in fact, in doing this, we have performed the work on the system that is equal. You can evaluate it easily from ideal gas law, is equal to KBT log 2, and this work has been dissipated into the reservoir. So the heat emission upon erasure of a bit is larger than or equal to KBT log 2, at least if the transformation is done in this way. And these conditions, say, for the performance of erasure, is known as the Landauer bound or the Landauer limit. Put it more generally, so in the words of Bennett, any logically irreversible manipulation of information. So here we are talking about the computationally reversible. So we are matching any logically reversible manipulation of information, such as the erasure of a bit of the merging of 2 computational paths, must be accompanied by a corresponding entropy increase in non-information bearing degrees of freedom of the information processes apparatus or of its environment. So this is a principle that connects the manipulation of information to thermodynamics. but still the process can be thermodynamically reversible if the total change in the entropy of the system, taking also into account the information bearing degrees of freedom, is equal to 0. That is, so there is no contradiction between performing a logically reversible manipulation of information and performing it in a thermodynamically reversible way. And this will have some implications later with the biological system. So just show how this has been illustrated by an experiment. And so this is a high precision experiment. What you have is that, again, it's a colloidal particle, and the colloidal particle say you by using optical tweezers you can mimic certain potential, in this case a two-well potential, and then you can use this potential, and you can use for instance in electric field manipulation to change the shape of the potential. And in this way, you can start from, for instance, from a situation in which a particle is with equal probability either left or the right, and then by changing the shape, so you break the symmetry, you let one of the minima go down and the other minimum remain high in such a way as to lead the whole probability distribution to the state, say, 1. And if you perform a completely symmetrical transformation in this way, what you get is that you start with probability distribution with equal probabilities between 0 and 1, and you end up again with a probability distribution with equal probabilities at 0 and 1. And then you evaluate what is the total work you have performed on the system in this way. So the fluctuating work is done by the distance by this expression. I hope you have seen it's just the continuous expression of the work analogous to the one we have seen before, that is given by the integral of the derivative of the manipulating parameter times the derivative of the potential evaluated at the actual point of the particle with respect to the manipulation parameter. And then you find that the asymptotic work is given by, say, in the limit of very long manipulation times with a given protocol, but diluted over longer manipulation times. This approaches a value with a correction of the order of the inverse of the manipulation time. The asymptotic value of the work you do is, say, in the experiment is about 0.05 units of kT for the symmetric case, in which you start from a symmetric probability, you end up with a symmetric probability. But if you look at the manipulation which ends up in one state with probability close to 1, you get a 0.71, which is larger than the K, which is larger than log 2. And so this is just a way, just looking at the mean of work with different manipulations. So what you will see is that with longer and longer manipulation, the variance is on the y side. With longer and longer manipulation, the variance of work decreases, and then also you see the mean decreases. But in the case of the symmetric manipulation, you end up close to 0. With the asymmetric manipulation, you end up close to something that is a bit larger than the log 2. So this is okay. This is probably clear. Just that the average value of the work is a function of the inverse time, and this is what I show. Okay, I think that I can stop here for the moment. and then we resume in 5 minutes. Is that okay?
So we resume after 5 minutes, you mean?
All right.
Okay. So actually, we started 15 minutes late. So in another 15-20 minutes, we can actually break for tea.
So 20 minutes and then, okay. So I can go on for 20 minutes.
So we can actually take a, if you're okay, we can take a 1 hour break now and come back after at 5.
Okay, 1 hour break now. All right.
Right. So we can resume at 5 o'clock.
All right. Okay.
Thank you.
Bye. Oh, wow.
We can have a photo session now outside.
All right. So see you later.
See you. I will. So please join using the second link that I sent you.